Actually, there are only three major topics in your fourth unit. First topic is your underdamped free vibrations. How do you derive the formula based on a trigonometric incoming disturbance, a periodic disturbance? Second topic was your dynamic magnifier. That what is a dynamic magnifier? Capital D is the let us place a 10 kg load on top of a spring. Now, if I start, I mean, an engine, let's say, best example, a 300 kilogram engine is placed on a chassis and the engine is not switched on. Okay, when the engine is at off condition, the load of the engine makes the chassis to deflect by 1 millimeter. Now, what will happen if I switch on the engine? You know, I have studied in the second unit, balancing of reciprocating masses. See, there will always be some unbalanced force left in the inside the system, swaying couple. A lot of forces are left behind, which is going to disturb your vehicle or the frame on which your engine is sitting. Now, this is going to create some additional deflection. The dynamic magnifier is the ratio between the static deflection and the dynamic deflection. Okay, initially my chassis bent by 2 millimeter. Now, after I switch on the engine, lot of dynamic forces come into the frame. Now my deflection is 4 millimeter. Okay, so what is dynamic magnifier? 4 by 2. 2. That is dynamic magnifier. Okay, that comes in the fourth unit. Now the next topic, the last topic of your fourth unit is so vibration isolation and transmissibility. This is the most important and the applied portion of your entire third and fourth unit. This is where you really use the subject, and we handle a lot of machines in our workshop. We have lathes, we have shaping machine, milling machine. So there are variety of machinery used everywhere in the manufacturing industries. If you see, if you go back to your manufacturing technology 2, first unit, mechanics of metal cutting, you would have come across a merchant's circle diagram where you have studied about three different forces that is encountered by a single point cutting tool. What are they? The cutting force, thrust force, and the feed force. Three different mutually perpendicular forces react on the job from the tool, and you get reaction forces on the tool. Now, this is a single point cutting tool. So, when you are trying to shear away the job, how does the material get removed when you are touching the, when you are turning in a lathe? How does it actually, how the chips form? How does it come out, and how do you get a smooth surface? All those things you have already studied. The material removal occurs on a theoretical shear plane, which is almost 45 degrees to your rake face, rake face of your tool. Okay, so now this shear plane keeps traveling in front of the cutting zone, and you are able to create a very fine smooth surface on the material by machining. Now, why do I tell you all these things? Now, imagine how much vibration comes in, and if you are unable to, you are having one of the best machines in the world, a very good German manufactured machine, but if you are unable to tap out all the vibration out of the machine, what will happen? Even though your machine is very good, but you have not properly balanced the machine and kept it on the foundation, what will happen is all the vibration and the chattering disturbances that creates that is going to shake your machine will be directly reflected on the surface roughness of your job. Okay, what will happen if your machine vibrates? Your tool post will vibrate, your tool will vibrate. Now that is going to be replicated on the surface of your workpiece. Okay, so if your machine is not exactly balanced, it is directly going to affect the surface roughness of your job. Your job will be rejected. Your client will not pay for your job. So this is one of the most important aspects of your third and fourth unit: vibration isolation and transmissibility. Okay, how good you are able to balance and isolate the vibration from your machine and make sure that it does not disturb your production. What is the use in producing thousands of components if it is not going to meet the requirement of your customer? Okay, so with that brief introduction, we will move into this. Okay, so a little consideration will show that when an unbalanced machine is installed on the foundation, it produces vibration in the foundation. Okay, so if you see, I'll show you 1 minute. You will go to the Google itself. I don't know how many of you have seen this, because I worked in a construction site before I came here. We used to install foundation bolts for all the machinery. So when you buy a machine, you don't just as it is. You don't keep it on the floor. What you do is you dig a very large pit. Okay, You dig a pit and put these foundation bolts inside. This will be almost 1 meter long. Okay, 1 meter long. These foundation bolts are kept along with the reinforcement. Steel rods are when you put a slab. What people are doing? They tie all the steel rods on the slab and then you put concrete. Right? Look at this image. So now what we do when I'm going to place a machine on a bed, the lathe is placed on a bed, a little bit raised from the floor. Correct. So below the floor, we take a very large pit. Actually, it goes up to 6 or 7 feet deep, even below the floor, and we place such an arrangement inside the floor, and we pour it fully with concrete. Okay. Now, this will be the floor level outside where you are standing, and this much of this portion will be raised, and the entire except the tip of these bolts, everything will be filled with concrete. Okay. Now your machine will be placed on top of this and will be bolted to the floor. Clear? Now this is called a foundation bolt. Foundation bolt is a bolt that comes from below. It will be filled with concrete. It is not just like that you buy a machine and place it on the floor. All large machines, even small lathes also, you put it on foundation bolts only. It is the right procedure. So when the machine vibrates, the foundation bolt has enough strength to hold the machine in place. I believe you understand this. Now, before you, instead of directly connecting the machine to the foundation bolt, in some places what we do, we, in order to prevent these vibrations and to minimize the transmission of forces to the foundation, machines are mounted on springs and dampers or on some vibration absorbing material, isolating material like rubber, cork. Many nowadays a lot of materials, artificial materials, synthetic materials are coming for absorbing the vibration. If you see in our dynamics lab, the rotating masses, reciprocating masses, balancing machines are placed on a rubber pad. Okay, so the last class we have seen gyroscope experiment in dynamics lab also, right? In the last Saturday, that equipment is also placed on a rubber pad so that all the disturbances created is not transmitted to the floor. Okay, what will happen if it is transmitted to the floor? The reaction forces will come back to the machine and it will start vibrating. Okay, nothing is going to happen to the floor. Why you are isolating it? If you hit a ball on a wall, what will happen to the wall? Nothing will happen. The ball will come back to you. Reaction force is very important. So to avoid the force being transmitted to the foundation doesn't mean that you are saving the foundation. You are saving the machine from the reaction forces. Okay. So it is going to create an enormous amount of vibration which is going to affect the quality of your product. So that is the whole idea of doing this. So with this in mind, we will move into the procedure of the derivation. Very briefly, I will tell you, and then we will see some problems and wind up today's class. In order to prevent these vibrations or minimize the transmission of forces to the foundation, machines are mounted on springs. So you saw the foundation bolts, right? Into that bolts, I will put some springs along with some damping material like cork washers, rubber washers, and on top of that I will place the lathe. Okay, so here you have to understand, we have to place the lathe and mark the holes, and then only I can create the foundation bolt. Wherever the bolt will be, what will happen if I pour the concrete and the bolts do not align with the lathe? It is a very big headache. Doing a foundation bolt work is a very crucial job, and it will be handed over to a very experienced engineer. Okay, I have been in that work, but I was not the in charge. I was just seeing. I was a part of the work. Okay. So let us consider a setup like this. A machine is there which is placed on. So if you see here, what is the whole idea of vibration isolation? What you do, the foundation is going to take all the forces. This is your ground, earth. Okay, this is your machine source of disturbance. Now I am going to put some springs and dampers in between, and I am going to isolate the vibrations and minimize the force transmitted to the foundation so that I don't get enormous amount of reaction force. Your machine will be at rest. Okay, so that you can produce enough quality of jobs, right? The arrangement is assumed to have 1 degree of freedom. In this diagram, for this derivation, we are actually, in reality, you will have 2 or 3 degrees of freedom depending on the number of axes your machine can move, right? If you go to a CNC vertical milling centers, VMC, they will specify what type of machine based on the number of degrees of freedom your tool can move. Okay, so there are 5 axis VMC, 6 axis VMC. So depending on the number of axes, your vibration degrees will change. Here for this fundamental derivation, we are going to consider only 1 degree of freedom for the vibrations. Okay, we assume that vibrations occur only in this way, either upward or downward. Okay, the lateral vibrations are neglected, right? And in this direction, is it like this direction vibrations are neglected. I consider only the z-axis vibrations, upward and downward. So all others are neglected because they are a little bit smaller in comparison. Okay, for simplicity. It may be noted that when a periodic disturbing force F cos omega t is applied on the machine of mass m supported by springs of stiffness S, then the force is transmitted by the means of springs and damper or dashpot to the fixed foundation. So I isolated, right? That's what I already told you. The ratio of force transmitted to the force applied is known as isolation factor or transmissibility ratio. Now this is very important. You are going to find out this factor in all the problems we are going to do today. So this is called as a transmissibility ratio. Okay, so what is transmissibility ratio? It is represented by the symbol epsilon. Okay, epsilon is equal to force transmitted to the, let us call force transmitted as Ft divided by whatever is the force you are going to apply, right? F cos omega t, you are having a periodic disturbance, right? F cos omega t. In that, what is the value of this F? What will happen if all these sinusoidal functions or cosine functions become maximum? Let us become, this becomes 1. What is the value of F? Maximum possible magnitude of the force you are applying, that is F. And that is a peak value, and then it is going to vary over time in a cosine function. Okay, starting at cos 0 1, cos 90 0, like that. Okay, right? So now Ft, epsilon transmissibility ratio is the ratio of force transmitted to the foundation to the force applied. We have discussed above that the force transmitted to the foundation consists of the two forces, spring force or elastic force, which is equal to stiffness of the spring into maximum amplitude. Okay, the maximum amplitude is the amount of stretch you are giving to the spring or compression you are giving to the spring. Both are possible. When vibration is going downwards, your spring will get compressed. When it moves back upwards, it will get stretched. So maximum extension of the spring either in the positive or negative direction is called X max. Most probably this value magnitude will be same. The direction only will keep varying, and multiplied by the stiffness will give you the amount of force applied on the springs, and the spring is going to get you back to the original position. That's why you keep the spring. This is called as the elastic component of the force. Okay, and the damping force. So you are having a damper in the middle of the spring, which is going to slow down the vibration. It won't allow the spring to vibrate violently. It will slow you down by means of a viscous medium, oil, or anything, something like that, some liquid. Okay, so that is given by C. Unit of C is Newton per meter per second. Okay, C multiplied by your angular frequency multiplied by this amplitude. So this is going to give you uh, some force. These two factors come into the force transmitted to the foundation. Since these two forces are perpendicular to one another, as shown in figure below, therefore they are therefore the force transmitted. Now, if you see how does a damper react to the incoming force? I have a piston filled with oil. Okay, I have a plunger. I mean a cylinder and a plunger arrangement. Okay, this is my plunger. I create some holes here, one hole here and one hole here. This entire system is closed, no oil can leak. Okay, so now what I do, I keep some load on here and I compress it. What will happen? This is basically a damper. How does a damper work? This oil will start flowing through the hole to this side, so that your downward stroke motion is slowed down. It is going to slow down. So what do you understand from this? If you apply a force like this, okay, your resistance offered by your oil will be in this direction. Correct? Oil is perpendicular to your force applied. Therefore, your C and S are perpendicular to each other. This is the force coming from your machine. This is your oil force, viscous force. They are perpendicular to each other as I have shown here. Okay, force, incoming force, oil force, right? So that's why they are perpendicular to each other. Now I am going to find a resultant out of these two, right? So force transmitted has two components. One is your elastic component and another one is the viscous component. Okay, so Sx. So we have told here what are all these two functions. Now bring it into the square root and add them, square them and add them to find the resultant. So Sx max the whole square plus C omega x max the whole square is going to give me the force transmitted to the foundation. Here. So Ft equal to, now x max whole square you can take outside the square root because they are common in both the terms. X max, since you are bringing it outside the square root, the square is eliminated. x max into root of s square plus c square omega square. Clear? So transmissibility ratio of epsilon is equal to, this is what I told you earlier, force transmitted divided by force applied. Okay, maximum value of the periodic force. Ft by F, so put a F here. The same expression divided by F. So we know that x max is equal to x naught into d. So this is what we have seen yesterday. Okay. So what did we see yesterday? X max equal to x naught into d. This is my static deflection and this is my maximum deflection. So this is what the initially I gave you an example when I started. You place an engine on a chassis, it deflects by 2 millimeter. You switch on the engine, due to all the unbalanced forces in the engine, the deflection increases from 2 to 4. Now again you switch off the engine, the deflection comes back to 2. Now, what is the ratio between the dynamically created deflection and the static deflection? 4 by 2, which is 2. The 2 is this dynamic magnification factor. Okay. Now, if we multiply the 2 to this initial deflection del or x naught value, I will get this x max. So, static deflection multiplied by dynamic magnification factor or dynamic magnifier will give me the value of x max, maximum amplitude. So, x max is nothing but, so f x naught is force applied divided by stiffness of the frame or the spring multiplied by dynamic magnifier. Okay. So epsilon equal to f by s into d into, so what is this? If you go back here, so what did I finally? This expression I am bringing here. So epsilon is equal to this expression you bring here. In place of x max, I am going to substitute. In place of x max, I am going to substitute whatever I have written there. So just keep this in mind. X max into square root of s square plus c square omega square by f. This I am bringing and putting here. Okay. So this is x max. X max into root of s square plus c square omega square by f. Same thing. Okay. Instead of x max, I am writing f by s into d. So I can cancel f. So this s I am going to bring it into the square root. So dynamic magnifier divided by s into, now bring the s into the square root. So what will happen? S square by s square plus c square omega square by s square. Dynamic magnifier square root of 1 plus c square omega square by s square. Okay. So now what is the expression for this dynamic magnifier? I am rearranging inside the square root with some mathematical manipulation technique. Okay, what is that? C by omega is this thing. Okay, you can put this as a whole square also. C omega s by whole square. Okay, so C omega by s equal to, I am deliberately multiplying 2 in the numerator and 2 in the denominator and also a m by m in the denominator only. Okay, so what will happen? 2m into s by m. So this 2c omega divided by 2m into, this is, so square root of s by m is omega n square. Okay, omega n. So if you eliminate the square root, it becomes omega n square. Omega n square. What is omega n square? S by m. So I am putting omega n square instead of s by m. Okay, so 2m omega n square. So in this 2m omega n square, I am taking 2m omega n into omega n. Okay, I know this is Cc, critical damping factor. Cc into omega n. So this is for, so making it familiar. See, even if you keep this as it is and substitute the values, you will get the same answer. So this is to make it in a familiar terms, we are changing the formula and rearranging. Okay, so if you know one of these values, you can easily find out. So what happens inside the bracket, it changes. 2c by cc into omega by omega n the whole square. These two are exactly same. Okay, the square root term and the square root term are exactly same, no difference. If you put all the numbers, you will get the same answer. Okay. So we know yesterday we have derived this dynamic magnifier. I have uploaded the video lecture. You go and see. So the formula for this D is 1 by square root of 2c omega by cc omega n whole square plus 1 minus. Okay. So you bring it and substitute here. What will happen? You will get this entire square root term in the denominator. The numerator will remain same. Okay. So I am substituting everything. Therefore, just the same numerator. The same thing is in here numerator. Okay, this entire thing you write in the numerator 1 plus 2c by cc into omega by omega and the whole square divided by this entire thing you write in the denominator. Okay, so root of 2c omega by cc omega n whole square plus omega. Okay. So this is the expression for epsilon. Actual formula for transmissibility ratio is square root of 1 plus 2c by cc into omega n whole square divided by whole square root of 2c omega by cc into omega n whole square plus 1 minus omega square by omega n square the whole square. So this whole square is including that 1 minus. Okay, because it is very difficult to put big brackets in this equation format. The entire font is becoming larger. This whole square is here. Clear? When the damper is not provided, C is equal to 0, what will happen to this expression? If C equal to 0, what will happen to the epsilon expression? When there is no damper, what will happen? C is 0, so this there is a C in multiplication, this entire term will vanish. Square root of 1, which is nothing but 1, the numerator will become just 1. Entire thing will vanish. You come here, this also will vanish because you have C in multiplication. Correct? 1 by 1 minus omega square by omega n square if you don't have a damper. The formula becomes very simple. Okay? So if C equal to 0, what will happen? Your formula becomes 1 by omega square, omega by omega n the whole square. It becomes a very simple formula if damping is negligible. Okay. From the above expression, we see that omega by omega n greater than 1, epsilon becomes negative. So in this expression, what will happen if this becomes greater than 1, you will get a negative way of epsilon value. What is the meaning of this negative epsilon value? How could it be negative? I am applying 10 Newton force. Okay. How can it, the transmission, at least the transmission should be 1%, not less than 1%. If you apply 100 Newton, at least 1% of Newton force should go to the foundation. What is the meaning of a negative epsilon? Negative epsilon, if you take a literal meaning, it means that some force comes from the foundation to your machine without even applying force. That is not the actual way to interpret it. Negative foundation means there is a phase difference of 180 degree between transmitted force and the disturbing force. That is the meaning of this negative. Okay. So if you apply a force in a perpendicular, it is getting transmitted in a different direction. That is the meaning of negative force. Okay. So value of omega by omega n must be greater than 2 if epsilon is to be less than 1. It is the numerical value of epsilon independent of any phase difference between the forces. So we will try to have a value of this greater than 2. Okay, and in most cases this is rearranged and written for sake of mathematical simplicity. It is this same thing is rearranged as, okay, same thing is rearranged as 1 by omega square, omega by omega and the whole square. We have did this in the third unit also. Okay, epsilon equal to 1 by omega and the whole square minus 1. How it is possible to do it like this? Because the difference between these two will be very small no matter how you put it. Okay, only the symbol will change. So the figure shown below is a graph for different values of damping factor. What is damping factor? Ratio of damping ratio to critical damping coefficient to critical damping coefficient is called damping factor. Okay, so if 100 Newton per meter per second is a critical value, I do only 5, my damping factor is 5%. Okay, so it's a figure, is a plot of damping factor to the variation of transmissibility ratio against omega by omega n. So what does it tell you? This plot tells you omega by omega n equal to square root of 2, then all the curves pass through the point epsilon equal to 1 for all values of damping ratio. Okay, so we should try to have a square root of 2 value for omega by omega n, which is going to give you not more than whatever force applied, not more than that will go to the foundation. Okay, less than square root of 2, then epsilon will be greater than 1. More force will go to the foundation than what you have applied. So that is an undesirable situation. Okay, when it is greater than 2, epsilon is less than 1 for all values of damping factor. So this is a very desirable situation. This shows that force transmitted through the elastic support is less than the applied force. Thus vibration isolation is possible only in the range of omega by omega n greater than root 2. Okay, so your omega is your actual spindle speed of your machine or the periodic disturbance speed, and omega n is the natural frequency of the particular material of the machine which is made up of. Now you should have, the machine should be operating at a very high speed compared to your natural frequency, because greater than 1, root 2 is 1.414, right? So your omega should be greater than omega n at least by 1.5 times. You should be operating the machine and the vibration order of the vibration should be very high frequency. Okay. We also see that from the curves in the above figure, I mean the below figure, that the damping is determined beyond omega by omega n greater than 2, and advantage is only in the region of omega by omega n less than 2. So all these things tells you that what sort of material I can choose for making the lathe bed cast iron. Why? Because cast iron has a very low natural frequency. I can operate the machine greater than that. It can absorb the vibration. Okay, so this is why you make choice of materials for absorbing vibration based on this. So every material has its own characteristic omega n. Now I know what is the spindle speed of my machine. I know what is the periodic disturbing force magnitude frequency. So based on that I choose the machine so that my ratio comes around greater than square root of 2 less than 2, 1.5 to 2, this ratio. Such a natural frequency you should have in your machine. That is how you choose your material. It is thus concluded that for vibration isolation, dampers need not be provided, but in order to limit the resonance amplitude, stoppers may be provided. Okay. So this is taken from your Kurmi textbook, 23.18 subtopic. Okay. So that completes.